Kinetic Molecular Theory, KMT. What's that? So all these particles are randomly moving with elastic collisions, right? And random energy, random moment. And then let's say this green and red dots are two reactants. They're moving around within this area, and then they colloid and make a reaction. Carbon plus oxygen makes CO2, let's say. Now, so there are a few things we need to see in order to have this reaction to happen. So oxygen and C should colloid this way to make CO2. If they colloid side by side, they may not make it. That's called the proper orientation. Now, if you have more and more particles, it's better for the reaction. If you have proper orientation, it's better for the reaction. And if you have more energy to reach the activation energy, that is better for the reaction. So actually it has to pass the activation energy, right? Remember, the hilltop is the activation energy. You need a little bit more to fall down. Now, so I took another one. Look at the beaker of glass with some water. Some of the water molecules have a lot of energy, and some of the water molecules have less energy. This type of distribution is called the Boltzmann curve. It's something like people in your class. Some of them are very tall guys, some of them are shorter guys, and there is a whole bunch medium. This medium, the average temperature is, average kinetic energy is actually the temperature of that sample. Now, y-axis is number of particles. It's also called the population. If 20-degree water sample, if I heat up to 30, what happens? They get more energy, kinetic energy. So the curve shifts to the right. As a result here, let's say I had X moles and this one also X moles. So that means you go from 30 to 20 to 30, your amount here is 2x in the Boltzmann curve. That's the whole point. That's what we are trying to look at. Now, if I go to 40 degrees, and even it will have even more, right? So that's the typical pattern when you, excuse me, when you heat a sample, the particles get more and more energy. So here is the activation energy. Why I'm putting that? Look at this one. In order to reach the hilltop, let's say it's a ball, you're pushing upward a mountain. So if you go to the hilltop, it's automatically fall down. So going onto the hilltop is actually similar to the activation energy. So let's say we have the activation energy here, 40 joules. Everything past that hilltop will go to the products. Everything before that will be reactants. So that's how we want to match this graph to the previous one. See this one, the hilltop is 40. Now if you have a catalyst, the magic, it will be the green line, which is, let's say, activation energy catalyzed. That would be, let's say, 35, right? So 35 would be somewhere here in the energy axis here. So that means whole lot of molecules are on the hilltop and they are becoming products. That's why we say every 10-degree increment will double the reaction rate. So it can be explained by Boltzmann.